So here in section 8.2 we'll look at the type of bonding called ionic bonding. Ionic bonding generally takes place between metals and nonmetals. Metals, of course, are on the left side of the periodic table over here. Nonmetals are located over here. There are some exceptions. Sometimes it's a metal and a polyatomic ion. Sometimes it's two polyatomic ions. But the ionic bond, as a rule, it generally contains a metal. In ionic bond, there's a very unequal sharing of electrons. As a matter of fact, electrons are mostly stolen or taken in ionic bonds. Electrons are transferred from one element to the other. And the way that they're transferred is to obtain the octet, or to have a noble gas configuration, if possible. For example, NaCl, a metal, sodium, over here on the left side of the periodic table, and a nonmetal, chlorine, over here on the right. So if we draw the Lewis electron dot structure of sodium, it would have one electron in its valence shell, 3s1 right here. And chlorine would have 7 electrons in its valence shell, right here. 3s2p5, adding up to 7. 1, 2, 3, 4, 5, 6, 7. So it's the s and p electrons that add together to give you your notation of the number of dots around it in the Lewis dot structure. Sodium would transfer its electron to chlorine, or give it away, or chlorine would steal the electron from sodium. Then sodium would then have a noble gas configuration, because if sodium loses an electron, it would now have 10 electrons and look like neon. Chlorine now becomes an ion, gaining 1 electron, and then would have a noble gas configuration like argon. This is an example of an ionic bond. 2 ions are now formed, one with 1 less electron, a cation, and one with 1 more electron, an anion. So once these are stuck together, there is a strength to that bond. And this ionic bond strength is governed by something called Coulomb's law of electrostatic attraction. Coulomb's law of electrostatic attraction has a unique formula to it. The electrostatic reaction is symbolized by the energy letter E, and that is equal to a constant K times Q1, Q2 divided by D. Now, the fancy name for E is the electrostatic lattice energy. So the energy associated with forming a lattice, positive and negative charged pieces, that are held together by a certain amount of energy. K is a constant. It's just a numerical value that you never have to memorize. And it's present in all of these, so just know that you can ignore it. Q1 and Q2 are the charges on the ions that come together. So for example, in our Na and Cl, to find the lattice energy that holds them together, it would be positive 1 and negative 1. So 1 and 1. And just use the magnitudes. Don't worry about whether it's positive or negative. You just put in 1 and 1 right there. And then D stands for the distance between the ions. And the distance between the ions is governed by its atomic size, which you learned back in chapter 7. So you need to know the trend of its atomic size. So we'll give 2 examples of lattice energy and determining which ones would be greater or less. First, let's take this example of 2 compounds, SCN versus KCl. Which one of these would have the larger or the bigger lattice energy? Well, we can ignore K because it's in the equation for both of these. We want to know E, we don't know that, and we don't actually have to put numerical values in, we just have to know whether it would be bigger or larger. So let's look on the periodic table and find the Q's, the charges on Sc and N. Sc is located right over here. Scandium. Scandium right here. It would be a metal, and it would be combined with nitrogen that has a -3 charge. And since there's one -3 charged species there, this must be +3. So the Q1 and Q2 for SCN must be positive 3 and negative 3. 3 times 3, that would be a magnitude of 9 on the top of this fraction. KCl, on the other hand, would have a positive value of 1 for potassium. Chlorine would have a negative 1 for chlorine, so positive 1 and negative 1. And so the Q1 times Q2, the top of this fraction would be 1. The top of this fraction right here would be 9. Now, rule number 1, charge rules are the most important. And so without even looking at the distance between these ions right here, 9 to 1, hands down, scandium nitride would have a much stronger lattice energy than KCl, just because it has 9 times as much charge on the top. And if you look at the lattice energy for some compounds in our book, here's scandium nitride right here at 7,500 or so in kilojoules per mole, versus something like potassium chloride, which is right here as 701. So almost 10 times as much, because it has that positive 3 and negative 3 right here. All right, let's look at a second example problem. Arrange in order of increasing lattice energies 3 compounds, NaF, CSI, and CaO. So remember rule number 1, charge rules are the most important, so let's find the charges of these that would go in Q1 and Q2. So sodium's positive 1, fluorine minus 1, cesium positive 1, iodine negative 1, calcium positive 2, oxygen negative 2. So right away we know the first. Rule number 1, charge first. Our biggest is going to be calcium oxide. That's going to have the largest lattice energy. Now the next two, we actually have to pay attention to the D, because remember sodium's plus 1, fluorine's minus 1, cesium's plus 1, iodine's minus 1. So the top of this fraction is the same. And remember, K is the same for every single one of these, so we can ignore it. Now we have to look at the distance. And so distance, if you forgot, is on page 302 of your textbook. So let's see if we can go back here just really quick. And let's take a look at the distance of these ions in case you don't remember the trend of the atomic sizes. And we can get the actual numerical values here if we want, but you need to know the trend. So sodium's right here, and then you can see that cesium would be much larger, 1.66 versus 2.0 for sodium versus cesium. So this would have a smaller number right here. This would have a larger number right here. And then we have to pay attention to the fluorine versus the iodine. And you can see once again fluorine is much smaller, 0.57, versus iodine, 1.39. And so this would have a much bigger diameter, or D right here, distance between the two. This one would be smaller. And now you just need to think mathematically for a second. If you have a bigger D right here, how does that affect this number on this side of the equation? So if you divide by a larger number, of course, you're going to get a smaller energy right here. And so our larger lattice energy would be NaF. And it probably makes sense in your mind, too, because they're closer together, so they stick together better, so they'd have a higher energy holding them together. And then CSI would be our one with the least or lowest lattice energy. So rule number 1, always look at the charges first. And then rule number 2, take a look at the distance. We'll come back with more ionic bonding pieces soon.